This is the AP Calculus AB Section 3.5 intro video. We're going to be talking about limits ad infinity. So these would be any limits that are of one of these two forms right here. Limit as x goes to infinity of f of x, or limit as x goes to negative infinity of f of x. And of course, as we talked about before, we of course never can actually reach infinity. We simply are looking at the pattern behavior of the function as x gets bigger and bigger without bound. One connection I want to make for you back to some of your pre-calc days is the idea that horizontal asymptotes really are defined by limits at infinity. So take a look at these two graphs down below. You can see that in both cases I've kind of illustrated a horizontal asymptote with the little red dotted lines. And so you can look at it. Let's just focus on the one on the left here for just a moment. We can see here that the question below is saying limit as x goes to infinity of f of x. And so limit as x goes to infinity, we're talking about the far right end of the graph. As we get way out to the far right end of the graph, what pattern are we seeing? And so, based on the dotted line, based on the graph, it looks pretty clear that the y values in that graph, as x gets really, really huge, are getting closer and closer to 2. We can kind of do the same idea with the graph on the right. This is saying the limit as x goes to negative infinity of f of x, and so this is talking about the extreme left end of the graph this time. So the idea here would be as x gets smaller and smaller and smaller, or further and further to the left, what are the y values of the function doing? What are they getting closer and closer to? Looks to me, hopefully the same to you, it looks like we're getting closer and closer to negative 3 as we get to the extreme right edge of the graph. So when we talk about limits at infinity, we're not really talking about at infinity. We're talking about as x gets really, really huge or really, really small. And I think it's important for us to see the connection back to the horizontal asymptotes. And of course, we're talking about the extreme ends of the graph, right? Extreme ends, plus or minus infinity being a good description of those extreme ends of the graph. Now we're going to take a look at a few examples of rules for limits at infinity. There's that little brown box at the top of this page. It's actually kind of a reiteration of some old pre-calc rules that you learned before. We're going to look at a couple of, and that brown box will apply. We'll certainly use that when we do our examples in class. So feel free to read the brown box. I don't need to read it for you. But we're going to look at these rules for limits at infinity. The first two here are very common. I'd say these are going to be used a lot. In both of these cases, the letter C stands for a constant, and then R stands for some exponent, and then X is our variable. So we're going to look at both of these here. The first one, limit as x goes to infinity of some constant over x to the r. So I'm just going to tell you right up that the answer to this one is 0. And I want to explain why that is. Let's just use some function that's a little more concrete that we can use to try to understand why this is. So take for example this function right here, 5 over x squared. That fits the pattern, right? It's a constant over x with some exponent on it. If I were to make a little table here as x goes to infinity, so I've got x's, I've got y's. So as x goes to infinity, let's say that x is, we'll start off real small here, let's say that x is 1. Well, then of course the output would be 5. Well, let's say that x is 10. So that would be 10 squared, that's 100, so it would be 5 100ths, that would be 0.05. Of course, we could get larger than that, right? We could say, well, how about 100? Well, 100 squared is 10,000, so that would be 5 10,000ths. So that would be 0.0005. Yeah, I believe that's correct. So you can see what's happening here. We could go with a bigger number. We could go with like 1,000,000 or 1,000,000,000 or something. That would, of course, be squared. But we can see that we're going from 5 to 0.05 to 0.0005. You can imagine if I just kept on putting larger and larger powers of 10, then the outputs would just be a whole bunch of zeros and then a 5, getting closer and closer to the actual value of 0. And then the answer to the other one here, the limit as x goes to negative infinity of x to the r, of c over x to the r, is also 0 for basically the same kind of reasoning We make a little table there. I encourage you, if you wanted to kind of explore this a little bit further, you could certainly make all the tables you want and see what happens with these. Of course, this only applies when the numerator is a constant and the bottom is x to the some whole number. This will be how it always works out. So this is a key fact that we'll use when I see you guys next time in class. There is a whole other branch of limits that we might see that are not quite so cut and dried, not quite so nice, where we could use those old pre-calc rules from before or the little rules right there. And so for that, we're going to look at something called relative growth rates. So there's going to come a time from every now and then that we're going to have to understand how this works in order to answer a question involving limits as x goes to infinity. So we're going to rank functions, like families of functions or types of functions, based on how fast they eventually grow. So our rankings go like this. X factorial. I don't know if you remember factorial from back in pre-calc. Usually used with like probability and counting type things. But x factorial grows faster than any other function besides x to the x. X to the x is the fastest. So x to the x would be like number 1 ranked, and x factorial would be number 2 ranked, I guess. So if you wanted to kind of compare maybe like a 10 to the x, which would be an exponential, with factorial, you could see that eventually, and in some cases like this one, it does take a while for x factorial to catch up and eventually pass 10 to the x, but we'd see eventually that x factorial does catch up and pass 10 to the x. This would be true for all factorials and exponentials. Well, the next ranking would be to say that any factorial, which would be a to the x, grows faster than any power of x, even like x to the, this looks like 1 billionth. So another way to say this would be to say that a to the x grows faster than any polynomial function as x approaches infinity. So if x to the x is number 1 and x factorial is number 2, that means exponentials, like a to the x, 5 to the x, 10 to the x, whatever, as long as a is positive, that would be ranking number 3. And then finally, polynomials like x to the a, even something that's got a really tiny exponent will eventually grow faster than any logarithmic function. So polynomials will always grow faster than any logarithmic function as we get bigger and bigger. So that means polynomials are number 4 ranked, and logarithms are the slowest. So those are the kind of the basic families of functions right there, and their rankings from fastest to slowest. And we'll use these when we do a couple of examples next time in class.